From the moment humanity first gazed up at the stars, we've been driven by an insatiable curiosity about what lies beyond our world. Ancient civilizations carved constellations into stone, guided by patterns they believed held divine messages. Centuries later, telescopes and spacecraft have taken us closer to understanding the vastness above. Yet for every answer we uncover, new questions emerge, questions that remind us just how much of the universe remains a mystery. Imagine this: in the infinite expanse of space, there are secrets so profound that even our brightest minds can't fully explain them. From invisible forces shaping galaxies to signals from unknown origins, these mysteries challenge everything we think we know. Today, we're diving deep into 25 unsolved mysteries of the cosmos phenomena that continue to baffle scientists and spark wonder in anyone who looks skyward. By the end of this journey, you'll see why the universe isn't just beautiful, it's also one of the greatest puzzles ever imagined. So buckle up, because we're about to explore the unknown together. Let's begin our cosmic journey with one of the most perplexing enigmas in modern astronomy: dark matter. Imagine a force that makes up roughly 85% of all matter in the universe, yet remains completely invisible to us. This is dark matter, an elusive substance that doesn't emit, absorb, or reflect light, making it nearly impossible to detect directly. Scientists first suspected its existence in the 1930s, when they noticed galaxies spinning far faster than expected based on their visible mass. Something unseen had to be holding these galaxies together, preventing them from flying apart. So why does dark matter matter so much? Its gravitational influence shapes entire galaxies, influencing how stars move and even affecting the large-scale structure of the universe itself. Without dark matter, galaxies like our own Milky Way wouldn't have formed in the way we observe today. Despite decades of research, though, scientists still don't know exactly what dark matter is made of. Some theories suggest it could consist of exotic particles called WIMP, weakly interacting massive particles, or perhaps sterile neutrinos. Others propose more radical ideas, such as modifications to our understanding of gravity itself. What makes dark matter so challenging to study is its sheer invisibility. It interacts only through gravity, leaving researchers to rely on indirect methods to uncover its secrets. Experiments deep underground, space-based observatories, and powerful particle accelerators are all part of the global effort to crack this mystery. But so far, dark matter continues to evade detection, reminding us just how much there is left to learn about the fabric of the cosmos. As we continue exploring this puzzle, the answers could redefine our understanding of the universe and our place within it. Shifting our cosmic lens from the mystery of dark matter, let's explore another invisible force that dominates the universe: dark energy. While dark matter holds galaxies together, dark energy seems to be tearing the entire cosmos apart. This enigmatic phenomenon is responsible for the accelerating expansion of the universe, a discovery so profound it earned a Nobel Prize in 2011. But what exactly is dark energy, and why does it continue to baffle scientists? To understand its significance, we must first consider the history of the universe. For decades, astronomers believed that the expansion of the universe, initiated by the Big Bang, would gradually slow down due to the pull of gravity. However, observations of distant supernovae in the late 1990s revealed something astonishing. The universe isn't just expanding, it's doing so at an ever-increasing rate. This acceleration suggests the presence of a repulsive force counteracting gravity on cosmic scales, which scientists have dubbed dark energy. Dark energy makes up approximately 70% of the total energy density of the universe, making it the dominant component shaping the fate of everything we know. Yet, unlike dark matter, dark energy doesn't clump or interact with ordinary matter. Instead, it appears to permeate all of space uniformly, exerting a constant outward push. The most widely accepted explanation for dark energy is Albert Einstein's cosmological constant, a term he initially introduced into his equations of general relativity to allow for a static universe. Ironically, Einstein later rejected this idea, calling it his biggest blunder. Today, however, the cosmological constant has been revived as a potential description of dark energy. But the story doesn't end there. Other theories propose quintessence, a dynamic form of energy whose density can change over time, or even modifications to our understanding of gravity itself. Each hypothesis brings us closer to unraveling the puzzle, yet none have provided definitive answers. What's certain is that dark energy remains one of the greatest unsolved mysteries in modern cosmology, holding the key to understanding not only the past but also the ultimate destiny of the universe. Will it expand forever into endless voids, or will some unknown force eventually halt this expansion? These questions drive researchers worldwide to probe deeper into the nature of this invisible powerhouse. Transitioning from the enigma of dark energy, let's now journey to another cosmic puzzle that has intrigued astronomers: fast radio bursts. These fleeting but incredibly powerful signals are among the most mysterious phenomena in the universe, emitting as much energy in a millisecond as the sun does in an entire day. But what exactly are they, and where do they come from? Fast radio bursts, or FRBs for short, though we'll avoid abbreviations here, are intense flashes of radio waves originating billions of light years away. First detected in 2007 by analyzing archival data from the Parkes Observatory in Australia, these bursts last only milliseconds before vanishing without a trace. Since then, scientists have identified hundreds of such events, each one leaving behind tantalizing clues about their origins. Theories abound regarding the source of these bursts. Some suggest they could be generated by neutron stars with extremely strong magnetic fields, known as magnetars. These highly energetic objects can produce bursts of radiation when their magnetic fields realign suddenly, releasing vast amounts of energy. Another possibility involves collisions between dense stellar remnants like black holes or neutron stars. In this scenario, the merger releases a burst of radio waves that travels across the cosmos until it reaches Earth. Yet, some researchers entertain even more speculative ideas. Could advanced extraterrestrial civilizations be responsible for these signals? While there's no evidence to support this hypothesis yet, the sheer mystery surrounding FRBs leaves room for imaginative possibilities. What's certain is that unraveling the secrets of fast radio bursts could reveal new insights into extreme astrophysical processes and the fundamental nature of our universe. As technology advances, observatories like CHIME in Canada and the Square Kilometre Array promise to detect more FRBs, helping us piece together this cosmic riddle. By studying their properties, such as how they disperse through intergalactic space, scientists hope to learn not just about the bursts themselves, but also about the medium through which they travel. This investigation may even help map the distribution of matter in the universe, offering answers to questions far beyond the bursts alone. With so much at stake, the quest to understand fast radio bursts continues, driving innovation and discovery in the field of astronomy. Shifting our focus now to the earliest moments of the universe, let's delve into two interconnected ideas that continue to challenge and inspire cosmologists: cosmic inflation and the multiverse theory. These concepts take us back to the very birth of existence, offering possible answers to some of the most profound questions about the cosmos. Cosmic inflation is a groundbreaking theory proposed in the early 1980s to explain the extraordinary uniformity and flatness observed in the universe today. According to this idea, just fractions of a second after the Big Bang, the universe underwent an unimaginably rapid expansion, a burst of growth far faster than the speed of light. This sudden stretching smoothed out any irregularities, creating the homogeneous conditions we see across vast distances. Inflation also helps solve the so-called horizon problem, which questions how regions of space too far apart to have ever interacted still share nearly identical temperatures. But here's where things get even more fascinating. The mathematics behind cosmic inflation suggests that this explosive growth might not have been a one-time event. Instead, it could still be happening elsewhere in regions beyond our observable universe. This leads directly to the speculative yet captivating concept of the multiverse. Imagine countless bubble universes, each with its own set of physical laws, continually forming within an ever-expanding cosmic foam. Our universe would simply be one among many, perhaps governed by different rules than those in other realms. While these ideas remain largely theoretical, they open up incredible possibilities for understanding the nature of reality itself. Experiments like studying patterns in the cosmic microwave background radiation provide tantalizing hints at whether inflation truly occurred and what implications it may hold for the existence of multiple universes. Whether or not the multiverse proves real, the journey to uncovering these secrets promises to deepen our appreciation for the wonders of the cosmos. Moving from the mind-bending possibilities of cosmic inflation and the multiverse, let's zoom in on a phenomenon much closer to home, or at least our galactic neighborhood. Enter the Great Attractor, a mysterious gravitational anomaly that has puzzled astronomers for decades. Imagine an invisible hand pulling not just our Milky Way but entire clusters of galaxies toward an unseen mass deep in the universe. This is no ordinary tug. It's a force so powerful that it influences the motion of millions of galaxies across vast cosmic distances. The Great Attractor lies somewhere in the direction of the Centaurus and Hydra constellations, roughly 250 million light-years away. However, its exact location remains elusive because it resides behind the dense plane of the Milky Way, where dust and stars obscure our view. Scientists believe this enigmatic region contains a concentration of mass far greater than what we can observe directly. Some estimates suggest it might be equivalent to tens of thousands of galaxies combined. But here's the catch: no one knows exactly what or who is causing this immense pull. One possibility is that the Great Attractor represents a colossal structure made up of dark matter, the same elusive substance responsible for shaping galaxies throughout the cosmos. Another theory proposes that it could be part of an even larger supercluster known as Laniakea, which encompasses our own Milky Way along with hundreds of thousands of other galaxies. Whatever the case may be, unraveling the mystery of the Great Attractor offers clues about how gravity operates on cosmic scales and sheds light on the hidden architecture of the universe. As researchers continue to refine their observations using advanced telescopes and simulations, the Great Attractor stands as yet another reminder of how much there still is to learn about the forces driving our universe. Its study highlights the intricate dance between visible and invisible matter, revealing a universe far more dynamic and interconnected than we ever imagined. Shifting our focus from the gravitational mysteries of the Great Attractor, let's delve into one of the most mind-bending puzzles in modern physics, the black hole information paradox. This conundrum sits at the intersection of two pillars of science: quantum mechanics and general relativity, and has puzzled some of the brightest minds for decades. Imagine this: when something falls into a black hole, it seems to disappear forever, crushed beyond recognition by its immense gravitational pull. But here's where things get tricky. According to classical general relativity, once an object crosses the event horizon, the point of no return, it is lost irretrievably. However, quantum mechanics tells us that information cannot simply vanish. It must be conserved somewhere in the universe. This creates a glaring contradiction between these two fundamental theories of nature. The paradox was first brought to light by Stephen Hawking in the 1970s when he discovered that black holes are not entirely black. Through a process now called Hawking radiation, they emit particles and slowly lose mass over time until they eventually evaporate completely. If this happens, what becomes of all the information that fell into the black hole? Does it truly disappear, defying the principles of quantum mechanics? Or does it somehow escape, encoded in the radiation emitted during evaporation? This debate has sparked intense discussions among physicists. On one side, proponents of the information loss argument suggest that the extreme conditions inside a black hole might destroy information permanently. Others argue for information preservation, proposing mechanisms such as holographic encoding or remnants left behind after a black hole's demise. Some even speculate about wormholes acting as conduits for retrieving lost data. Understanding the black hole information paradox could revolutionize our comprehension of both quantum mechanics and gravity. Solving it may require developing a unified theory of quantum gravity, bridging the gap between the smallest scales of reality and the vastness of cosmic phenomena. As scientists continue to explore this frontier, the answers remain tantalizingly out of reach, reminding us just how much we still have to discover about the fabric of space and time. Transitioning from the enigmatic depths of black hole physics, let's journey outward to examine a peculiar feature in the cosmic microwave background radiation, the so-called axis of evil. This anomaly challenges one of the most fundamental assumptions about our universe, its isotropy or uniformity in all directions. When scientists first mapped the leftover glow from the Big Bang using satellites like COBE and later WMAP, they expected to see a nearly perfect homogeneity across the sky. However, what they discovered instead was surprising a distinct alignment in certain temperature fluctuations that seemed to stretch along a specific axis. The term axis of evil was coined by cosmologist Joe Megiddo due to the unsettling implications it raises for cosmological models. According to standard theory, the early universe should have expanded uniformly, leaving behind random variations in temperature. Yet, these particular patterns suggest an unexpected preference for a particular direction in space. Some researchers speculate this could hint at unaccounted for systematic errors in how we measure the CMB, while others entertain more radical ideas, such as modifications to general relativity or even the existence of preferred directions in the cosmos. What makes the axis of evil particularly intriguing is its potential to disrupt foundational principles of modern cosmology, including the Copernican principle, which states that Earth occupies no special place in the universe. If confirmed, this anomaly might imply that large-scale structures in the universe are not entirely symmetrical after all. Such revelations would force us to reconsider long-held beliefs about the nature of space and time, potentially opening doors to new theories that better explain the complexities of our cosmic environment. While the evidence remains inconclusive, the axis of evil continues to spark lively debate among astronomers and physicists alike. It serves as yet another reminder of how much there still is to uncover about the intricate workings of the universe, and how every discovery can lead to profound questions waiting to be answered. Shifting our focus from the puzzling axis of evil, let's delve into another cosmic conundrum that has left scientists scratching their heads: the lithium problem. This mystery revolves around a fundamental inconsistency between the amount of lithium we observe in the universe and what theoretical models predict based on Big Bang nucleosynthesis. Big Bang nucleosynthesis is the process by which the earliest elements, hydrogen, helium, and trace amounts of lithium, were formed just moments after the universe came into existence. According to this well-established theory, the abundance of these primordial elements should match what we measure today. However, when astronomers point their telescopes toward ancient stars and interstellar clouds, they find significantly less lithium than expected. In fact, the observed levels are only about 1/3 of what calculations suggest should exist. This discrepancy isn't trivial. It challenges some of the core assumptions about how the universe evolved in its infancy. Scientists have proposed several explanations for the lithium problem, but none have been universally accepted yet. one possibility is that our understanding of stellar processes might be incomplete. Stars could destroy more lithium than current models account for, skewing the measurements we make today. Alternatively, there may be unknown physical phenomena at play during the first few minutes of the universe's history that altered lithium production in ways we don't fully grasp. Another intriguing hypothesis suggests that dark matter particles could interact with normal matter in such a way as to affect lithium synthesis. While speculative, this idea opens up exciting avenues for research, potentially linking two of the biggest mysteries in cosmology: dark matter and the lithium problem. What makes this issue even more fascinating is its implications for other areas of astrophysics. Solving the lithium problem could lead to refinements in both particle physics and cosmological theories, shedding light on the conditions present in the early universe. As technology advances and new data emerges, researchers hope to unravel this enigma, bringing us closer to a comprehensive picture of the cosmos' origins. For now, though, the lithium problem stands as a tantalizing reminder of how much there still is to learn about the fundamental building blocks of the universe. Moving on from the lithium problem, let's shift our gaze to another dazzling yet perplexing phenomenon in the cosmos: gamma-ray bursts. These are some of the most powerful explosions ever recorded, releasing more energy in a few seconds than our Sun will produce over its entire 10 billion-year lifetime. Gamma-ray bursts, or GRBs as they're often referred to by scientists, occur somewhere in the universe about once per day, and their brilliance can outshine entire galaxies. The sheer intensity of these bursts raises an obvious question: what could possibly generate such extreme energy? While astronomers have proposed several theories, the exact mechanisms behind GRBs remain one of the great unsolved mysteries of astrophysics. Broadly speaking, there are two main types of gamma-ray bursts: short-duration bursts lasting less than 2 seconds, and long-duration bursts that persist for several minutes or even longer. Each type likely originates from different cosmic events. For short bursts, the prevailing hypothesis involves the collision of neutron stars or black holes within binary systems. When these incredibly dense objects merge, they unleash vast amounts of energy in the form of gamma rays. On the other hand, long bursts are thought to arise from the cataclysmic deaths of massive stars. In this scenario, a star collapses under its own gravity, forming a black hole while simultaneously launching jets of material at nearly the speed of light. These jets collide with surrounding matter, producing the intense burst of radiation we detect as a gamma-ray flash. Despite these insights, significant uncertainties remain. For instance, why do some bursts appear closer to home, while others seem to originate billions of light-years away? Could there be entirely new types of celestial phenomena responsible for these bursts that we haven't discovered yet? Moreover, understanding the precise conditions required for each type of burst continues to challenge researchers, as many factors, from magnetic fields to relativistic effects, play crucial roles in shaping these explosive events. Gamma-ray bursts also serve as valuable tools for studying the early universe. Since they occur across vast distances, detecting them allows scientists to peer back in time to observe conditions shortly after the Big Bang. By unraveling the secrets of GRBs, we may unlock answers not only about their origins but also about the fundamental nature of the cosmos itself. As telescopes grow more sensitive and data analysis techniques advance, the hope is that these brilliant enigmas will reveal their truths, bringing us one step closer to comprehending the universe's most violent and mysterious processes. Shifting our focus from the explosive power of gamma-ray bursts, let's now journey into one of the most tantalizing mysteries in the search for extraterrestrial intelligence: the WOW signal. Detected on August 15, 1977 by astronomer Jerry Amon using Ohio State University's Big Ear radio telescope, this unusual signal stood out like nothing ever observed before or since. The signal lasted for 72 seconds and appeared to originate from the constellation Sagittarius, near a star called Tau Sagittarii. What made it so remarkable was its intensity and narrow frequency band, characteristics that closely matched what scientists would expect from an artificial transmission rather than a natural cosmic event. Intrigued by its potential significance, Eamon famously wrote, "Wow," in the margins of the printout, giving the signal its iconic name. Despite extensive follow-up searches, no repeat of the signal has ever been detected. This lack of confirmation raises numerous questions. Was it truly a message from an alien civilization, or could it have been something far more mundane, such as interference from Earth-based sources or even a previously unknown astrophysical phenomenon? Over the decades, various theories have emerged, ranging from space debris reflecting Earth's own transmissions back at us, to emissions from comets passing through our solar system. However, none of these explanations fully account for the unique properties of the WOW signal. What makes the mystery even more intriguing is the context in which it occurred. At the time, the Search for Extraterrestrial Intelligence SETI program was still in its infancy, relying on limited technology compared to today's advanced instruments. Yet, the WOW signal remains one of the strongest candidates for evidence of intelligent life beyond Earth, though unverified. As we continue to explore the cosmos with increasingly sophisticated tools, the WOW signal serves as both a reminder of how much we don't yet understand and a beacon of hope for those searching for answers. Could there be other signals waiting to be discovered, hiding among the vast sea of cosmic noise? Or will the WOW signal forever remain a solitary enigma, teasing us with the possibility of contact just out of reach? Moving from the intriguing case of the WOW signal, let's now direct our attention to another cosmic enigma that has puzzled astronomers for years. Tabby's star, officially known as KSE 8,462,852. This star, located in the constellation Cygnus, first gained fame in 2015 when scientists noticed its unusual dimming patterns. Unlike typical stars, which exhibit predictable fluctuations in brightness, Tabby's star dims dramatically at irregular intervals, sometimes by as much as 22%. Such significant dips cannot be explained by conventional astronomical phenomena like planetary transits or stellar activity. The peculiar behavior of Tabby's star sparked a flurry of hypotheses, ranging from the plausible to the speculative. One widely discussed theory involves a massive dust cloud orbiting the star. These clouds could potentially block out light, causing the observed dimming. However, this explanation struggles to account for the star's inconsistent and erratic dimming schedule. Another possibility points to shattered comets or asteroid fragments swarming around the star, but again, this falls short of fully explaining the data. Perhaps the most captivating hypothesis is the idea of alien megastructures. Some have proposed that an advanced extraterrestrial civilization might be constructing massive structures such as Dyson spheres to harness energy from the star. While thrilling, this theory lacks concrete evidence and remains purely speculative. Critics argue that the likelihood of such advanced civilizations existing and coincidentally being near Tabby's star is astronomically low. Despite extensive observations with modern telescopes, no definitive answer has emerged. What we do know is that Tabby's star continues to defy easy explanations, challenging our understanding of celestial mechanics and sparking debates across the scientific community. As research progresses, one thing is certain: Tabby's star will remain a focal point for those eager to uncover its secrets, whether they lie in the realm of natural astrophysics or the tantalizing prospect of intelligent life beyond Earth. Could it hold the key to unlocking mysteries about distant civilizations, or does the answer lie closer to home within the complexities of space debris? Only time and further investigation will tell. Transitioning from the enigma of Tabby's star, we now turn our gaze to another cosmic puzzle that has perplexed scientists for decades: the missing baryons problem. Baryons, which include protons and neutrons, make up the ordinary matter we interact with everyday stars, planets, and even ourselves. According to the Big Bang theory, these particles should account for about 5% of the total mass energy content of the universe. However, when astronomers add up all the observable baryonic matter in galaxies, stars, and interstellar gas clouds, they find that a significant portion is unaccounted for. This discrepancy raises an intriguing question. Where are the missing baryons hiding? One leading hypothesis suggests that the missing baryonic matter resides in vast filaments of hot gas stretching across the universe. These filaments form part of the cosmic web, an intricate network connecting galaxies over immense distances. The gas within these structures is thought to be so diffuse and hot, reaching temperatures of millions of degrees, that it emits primarily in X-rays, making it extremely challenging to detect with current technology. Despite this difficulty, researchers have made strides in identifying some of these elusive filaments using advanced telescopes and computational models. For instance, observations by space-based observatories like the European Space Agency's XMM Newton and NASA's Chandra X-ray Observatory have provided tantalizing glimpses of these hot gas filaments. By analyzing the faint X-ray emissions from these regions, scientists can estimate their density and temperature, piecing together clues about the distribution of baryonic matter throughout the cosmos. Additionally, simulations run on supercomputers help predict how these filaments might behave under different conditions, offering valuable insights into their role in shaping the large-scale structure of the universe. The search for missing baryons not only addresses a fundamental gap in our understanding of the universe, but also sheds light on processes such as galaxy formation and evolution. As new instruments come online and observational techniques improve, we may finally uncover the full extent of the cosmic web and resolve this long-standing mystery. Could solving the missing baryons problem reveal secrets about the early universe and its development over billions of years? The quest continues, fueled by curiosity and driven by cutting-edge science. Shifting our focus now to a mystery that puzzled scientists for decades, let us delve into the fascinating case of the Pioneer anomaly. In the late 20th century, humanity sent two intrepid spacecraft, Pioneer 10 and Pioneer 11, on groundbreaking missions to explore the outer reaches of our solar system. These probes provided invaluable data about Jupiter and Saturn before venturing into the vast unknown beyond the planets. However, as they traveled farther from the Sun, an unexpected phenomenon began to emerge. Both spacecraft appeared to be slowing down at a rate that defied explanation. Initially, scientists thought this deceleration might be due to gravitational forces or other known effects. Yet after extensive analysis, it became clear that no conventional explanation could account for the discrepancy. The probes were slowing more than expected by a tiny but consistent amount. This puzzling behavior sparked intense debate among physicists and astronomers, who speculated about everything from new physics to dark matter influencing the spacecraft. The mystery lingered until researchers conducted a meticulous review of decades-old data. Painstakingly reconstructing the journeys of the pioneers, they discovered that the deceleration was likely caused by heat radiating unevenly from the spacecraft systems. Specifically, the electrical power source and propulsion units emitted thermal energy in directions that subtly affected the probe's motion. Advanced modeling confirmed that these thermal effects were sufficient to explain the observed anomaly. While the resolution may not have unveiled revolutionary new laws of physics, the process of unraveling the Pioneer anomaly highlighted the importance of precision in space exploration. It also demonstrated how even seemingly mundane factors like heat distribution can play crucial roles in understanding complex phenomena. As we continue to push the boundaries of what we know about the universe, cases like the Pioneer anomaly remind us that sometimes the answers lie in the details we least expect. Venturing further into the cosmos, we now encounter two remarkable interstellar objects that have captivated scientists and space enthusiasts alike, Oumuamua and Borisov. These cosmic wanderers represent our first direct glimpses of visitors from other star systems, offering tantalizing clues about the vast universe beyond our own. In 2017, astronomers detected the first known interstellar object named Oumuamua. This mysterious traveler displayed unusual characteristics unlike anything observed in our solar system. Shaped like a cigar or perhaps a pancake, depending on interpretations, it moved at incredible speeds and exhibited non-gravitational acceleration, suggesting forces beyond typical orbital mechanics might be at play. Some speculated that its peculiar behavior could indicate an artificial origin, though most scientists lean toward natural explanations such as outgassing or unique material composition. Less than 2 years later, in 2019, another interstellar visitor entered our neighborhood, this time Comet Borisov. Unlike Oumuamua, Borisov was unmistakably cometary in nature, exhibiting a glowing coma and tail as it approached the Sun. Detailed observations revealed striking similarities between Borisov's composition and comets found within our own solar system, hinting at common processes across different star systems. Yet its journey through space also highlighted differences, suggesting that conditions elsewhere may vary significantly from those familiar to us. Together, these two objects open a window into the diversity of celestial bodies scattered throughout the galaxy. By studying them, researchers gain insights into how planets form around distant stars, the materials available in alien systems, and even potential hazards posed by similar objects passing near Earth in the future. While much remains unknown, each discovery brings us closer to understanding the intricate tapestry of the universe and humanity's place within it. As telescopes grow more advanced, we eagerly anticipate uncovering additional interstellar guests, ready to reveal further secrets hidden among the stars. With each new observation, the story of our cosmos becomes richer and more fascinating, inviting all who gaze skyward to ponder the infinite possibilities awaiting discovery. Next, we explore yet another cosmic puzzle, the enigmatic cold spot that challenges our understanding of the universe's origins and structure. Shifting our focus to another cosmic enigma, let us delve into the mysterious cold spot, a peculiar feature in the cosmic microwave background radiation that has puzzled scientists for years. Discovered in 2004, this unusually large and cold region stretches across billions of light years, appearing colder than the average temperature of the surrounding space. It stands out as an anomaly in the otherwise uniform pattern of leftover radiation from the early universe. The cold spot challenges our understanding of the cosmos because it defies the standard model of cosmology, which predicts a relatively smooth distribution of matter and energy in the universe. Several theories have been proposed to explain its existence, ranging from the mundane to the extraordinary. One explanation suggests that it could result from a supervoid, an immense region of space containing fewer galaxies than expected. However, recent studies cast doubt on this idea, as such a void would need to be extraordinarily large and unlikely based on current observations. Another intriguing hypothesis involves a cosmic texture, a remnant of the universe's earliest moments when quantum fluctuations were stretched across vast distances during cosmic inflation. These textures could create localized distortions in the cosmic microwave background, potentially accounting for the cold spot. Yet, this theory remains speculative and requires further evidence to support it. Perhaps the most fascinating possibility ties the cold spot to parallel universes. In the context of the multiverse theory, some physicists propose that it might represent a collision between our universe and another, leaving an imprint in the form of cooler temperatures. While captivating, this idea is highly speculative and lacks direct observational proof. Understanding the cold spot holds significant implications for cosmology, as it could reveal gaps in our knowledge about the universe's structure and evolution. As researchers continue refining their instruments and techniques, they hope to uncover more clues about this mysterious phenomenon. By studying the cold spot, we edge closer to unraveling the secrets of the cosmos while acknowledging how much still lies beyond our grasp. Moving on to another captivating cosmic puzzle, let us turn our attention to the methane mystery on Mars, a question that has intrigued scientists and space enthusiasts alike. Methane, a gas often associated with biological processes on Earth, has been detected in fluctuating levels in the Martian atmosphere. These findings have sparked intense debates about their origin and implications for the red planet's potential habitability. Methane concentrations on Mars are not constant. They vary both seasonally and geographically. Observations from spacecraft orbiting Mars, as well as data collected by rovers on its surface, reveal spikes in methane levels at certain times and locations. For instance, the Curiosity rover detected sudden bursts of methane in Gale crater, followed by periods of near-zero readings. This erratic behavior adds complexity to understanding the source of these emissions. Two primary theories compete to explain this phenomenon: geological versus biological processes. On one hand, some researchers suggest that volcanic activity deep beneath the Martian surface could release methane trapped in rocks over millions of years. Another possibility involves serpentinization, a chemical reaction between water and iron-rich minerals which can produce methane as a byproduct. While plausible, these explanations require evidence of ongoing geological activity, something that remains elusive given current knowledge of Mars' relatively stable interior. On the other hand, the tantalizing prospect of microbial life cannot be dismissed. Methane is frequently produced by methanogenic organisms on Earth, leading many to speculate whether similar microbes might exist on Mars. If true, this would represent a groundbreaking discovery proving that life, or at least its remnants, could persist in extreme environments beyond our planet. However, confirming such an idea demands robust proof, as non-biological mechanisms could also account for the observed methane variations. Complicating matters further, methane on Mars breaks down quickly due to exposure to ultraviolet radiation. This means any detected methane must have been released relatively recently, raising questions about storage mechanisms or continuous production sources. Scientists continue refining models and gathering data to distinguish between these competing hypotheses. The methane mystery on Mars underscores the importance of continued exploration and research. As new missions arrive at the red planet equipped with advanced instruments, we edge closer to unraveling this enigma. Whether the answer lies in geology or biology, solving this puzzle will deepen our understanding of Mars and its potential role in the search for extraterrestrial life. Shifting our cosmic focus to another fundamental question, let us delve into the intriguing case of the vanishing proton decay experiment, a quest that once promised groundbreaking revelations about the nature of matter itself. In the early days of particle physics, scientists theorized that protons, long considered stable building blocks of atoms, might not be immortal after all. If true, this would challenge everything we knew about the universe's structure and longevity. Proton decay became a central topic in the development of grand unified theories GUT, which aimed to merge three fundamental forces: electromagnetism, strong nuclear force, and weak nuclear force into a single framework. According to these theories, protons could eventually break down into lighter particles such as positrons or pions, though with an extraordinarily long half-life measured in trillions upon trillions of years. Detecting such a rare event required massive detectors capable of monitoring vast amounts of matter over extended periods. One notable attempt was Kamiokande, located deep within a Japanese mine to shield against background radiation. Scientists filled enormous tanks with water, reasoning that if a proton decayed, it would emit detectable flashes of light known as Cherenkov radiation. Similar experiments emerged globally, including IMB in the United States and Baxen in Russia, all designed to capture the elusive signature of proton disintegration. Despite decades of effort and meticulous observation, no conclusive evidence of proton decay has ever been found. This absence raises profound questions. Are protons truly eternal? Or do current JUTs require refinement? Perhaps future discoveries will reveal new insights into supersymmetry or string theory, offering alternative explanations for why protons remain stubbornly intact. While disappointing for some researchers, the failure to observe proton decay highlights the complexity of probing the universe's most fundamental truths. It serves as a reminder that science thrives on perseverance and adaptability, pushing boundaries even when answers prove elusive. As technology advances, perhaps one day we'll unlock the secrets hidden within the tiniest particles, shedding light on the very fabric of existence. Until then, the mystery endures, inviting speculation and inspiring further exploration. Transitioning from the enigma of proton decay, let us now journey to the outer edges of our solar system, where another cosmic puzzle awaits: the Kuiper Cliff. This phenomenon refers to the sudden and unexpected drop-off in the number of objects beyond the Kuiper belt, a region of icy bodies extending far beyond Neptune's orbit. Astronomers had long expected this area to be densely populated with countless small celestial bodies left over from the solar system's formation. However, as observations improved, they uncovered a startling reality. Beyond a certain distance, the density of these objects sharply declines, forming what scientists call the Kuiper Cliff. This abrupt cutoff raises significant questions about the solar system's architecture and evolutionary history. One hypothesis suggests that an undiscovered massive object, perhaps a distant planet or a dwarf star, might have influenced the distribution of Kuiper belt objects through gravitational interactions. Another theory posits that the cliff could result from the early dynamics of the solar system, during which migrating gas giants like Jupiter and Saturn reshaped their surroundings, clearing out debris in certain regions. Yet, neither explanation fully accounts for the observed behavior, leaving room for alternative ideas. For instance, some researchers speculate that the Kuiper Cliff may reflect the boundary of the solar system's original protoplanetary disk, hinting at constraints on its size and composition during formation. Others propose that external forces, such as passing stars or interstellar clouds, could have stripped away material from the outer reaches of the solar system. While current technology limits our ability to probe deeper into this mystery, future missions and advancements in telescopic observation hold promise. By unraveling the secrets of the Kuiper Cliff, we may gain profound insights into the processes that shaped our cosmic neighborhood billions of years ago, further illuminating the intricate dance of gravity and matter that defines the universe. As exploration continues, the Kuiper Cliff remains a tantalizing clue waiting to be deciphered. Venturing now into the breathtaking beauty of deep space, let's turn our attention to one of the most visually striking cosmic phenomena, the Red Rectangle Nebula. Located roughly 2,300 light-years away in the constellation Monoceros, this celestial wonder is not only a feast for the eyes but also a profound mystery for astronomers. What makes the Red Rectangle Nebula so intriguing is its almost perfect rectangular shape, an unusual feature in the typically chaotic and asymmetrical universe. Unlike most nebulae, which appear as irregular clouds of gas and dust, the red rectangle exhibits sharp, geometric lines that seem meticulously crafted. Scientists believe this unique structure arises from the interaction between a dying star at its center and the surrounding material it ejects. The prevailing theory suggests that the central star, nearing the end of its life cycle, expels layers of gas and dust in opposing directions. However, what gives the nebula its rectangular appearance is thought to be caused by a dense disk of dust surrounding the star, which forces the ejected material into specific pathways. This creates the illusion of a series of nested rectangles or X-shaped patterns when viewed from Earth. Yet, the symmetry doesn't stop there. The red rectangle also features stunning beams of light radiating outward, forming a dazzling display akin to a cosmic diamond necklace. These beams are believed to result from scattering effects within the nebula's dusty environment, adding another layer of complexity to its already enigmatic nature. While current models offer plausible explanations for the nebula's formation, many questions remain unanswered. For instance, why does the central star exhibit such precise behavior compared to other similar systems? Could unseen companions or additional gravitational influences play a role? As telescopes grow more powerful, researchers hope to uncover further clues about this remarkable object, shedding light on both its origins and the universal processes shaping such intricate structures. By studying the Red Rectangle Nebula, we gain valuable insights into stellar evolution and the delicate interplay of forces governing the cosmos. Shifting our focus now to one of the most fundamental questions in cosmology, let's delve into the puzzling discrepancy surrounding the universe's age. While it might seem like a straightforward measurement, scientists have encountered a growing tension between two primary methods used to estimate this cosmic timeline. On one hand, we have the cosmic microwave background radiation, often referred to as the afterglow of the Big Bang. By studying this faint glow, researchers can calculate how long ago the universe began its expansion. Current estimates from this method suggest the universe is approximately 13.8 billion years old. This value aligns well with theoretical models of cosmic evolution and has been corroborated by observations made using advanced telescopes such as the Planck satellite. However, there's another approach that measures the distances and motions of nearby galaxies. These measurements rely on what astronomers call standard candles, objects whose intrinsic brightness is known, allowing their distance to be calculated based on how dim they appear from Earth. Using this technique, scientists arrive at a slightly different number for the universe's age, around 12.5 billion years. At first glance, the difference may seem small, but when dealing with such vast timescales, even minor discrepancies carry significant implications. What could explain this gap? Some propose that our understanding of dark energy, the mysterious force driving the universe's accelerated expansion, might need refinement. Others suggest that previously unknown particles or interactions could be influencing these measurements. A more radical idea involves rethinking some foundational assumptions about the universe's structure and behavior. This disagreement highlights just how much there still is to learn about the cosmos. As new technologies come online, capable of probing deeper into space and time, we may uncover evidence that resolves this enigma. Until then, the question remains, is the universe older or younger than we think? Or do we need an entirely new perspective to reconcile these conflicting results? Moving on to another intriguing cosmic enigma, let's explore the mysterious radio signals originating from the heart of our own galaxy. At the center of the Milky Way lies a region teeming with energy and activity, home to Sagittarius A, the supermassive black hole that anchors our celestial neighborhood. Amidst this chaotic environment, astronomers have detected bursts of radio waves that defy easy explanation. These galactic center radio bursts are unlike anything observed elsewhere in space. They appear sporadically, lasting only fractions of a second before vanishing without warning. What makes them particularly puzzling is their lack of any clear pattern or repetition. Unlike fast radio bursts from distant galaxies, which sometimes follow predictable cycles, these signals seem entirely random. Scientists have proposed several theories to account for their origin, but none has been conclusively proven. One hypothesis suggests that these bursts could result from interactions between the supermassive black hole and nearby objects such as neutron stars or white dwarfs. Another possibility involves exotic phenomena like dark matter annihilation or even undiscovered particles emitting radiation at specific wavelengths. Some researchers entertain the idea that these signals might stem from advanced extraterrestrial civilizations attempting to communicate across vast distances. Despite cutting-edge observational tools and years of study, the true nature of these radio bursts remains elusive. The challenge lies not only in detecting them, but also in pinpointing their exact location within the densely packed galactic core. As new telescopes come online with greater sensitivity and resolution, scientists hope to gather more data about these mysterious emissions. Until then, the question lingers: are these signals echoes of cosmic processes we don't yet understand, or do they hint at something even more extraordinary? Whatever the answer may be, unraveling this mystery promises to deepen our understanding of the universe's most dynamic regions. Mystery 25. The formation of supermassive black holes. Conclude the list with the mystery of how supermassive black holes form so quickly in the early universe, shifting our focus to one of the most profound enigmas in astrophysics. Let's delve into the formation of supermassive black holes and their rapid emergence in the young universe. These cosmic titans, often millions or even billions of times more massive than our Sun, sit at the centers of galaxies, influencing their structure and evolution. Yet their origins remain shrouded in mystery, particularly given that some of these giants existed just a few 100 million years after the Big Bang. The challenge lies in explaining how such immense objects could form so swiftly. Traditional theories suggest they might have evolved from smaller stellar black holes, which gradually grew by devouring surrounding matter. However, this process would likely take far longer than the timeline allows. Another possibility involves direct collapse, where vast clouds of gas collapse under their own gravity to create seed black holes much larger than those formed from individual stars. This mechanism could potentially accelerate their growth, but it still raises questions about the conditions necessary for such collapses to occur. Adding complexity to the puzzle, scientists have also explored the role of dark matter in fostering supermassive black hole formation. Some models propose that dense concentrations of dark matter could provide additional gravitational pull, hastening the aggregation of ordinary matter into black holes. Furthermore, exotic scenarios involving primordial black holes, those born shortly after the Big Bang, are occasionally considered, though evidence supporting this hypothesis remains elusive. What makes this mystery especially intriguing is its implications for galaxy evolution. The intimate relationship between supermassive black holes and their host galaxies suggests that understanding one may unlock secrets about the other. As advanced telescopes peer deeper into the cosmos, capturing light from ever earlier epochs, researchers hope to gather critical clues about these colossal entities. Solving this riddle promises not only to illuminate the life cycle of black holes, but also to deepen our comprehension of the universe's earliest days and its grand architectural principles. Building on the mystery of supermassive black holes, let's explore how their formation and presence profoundly influence galaxy evolution. This intricate relationship between these cosmic giants and their host galaxies is often referred to as coevolution, suggesting that the growth of a galaxy is closely tied to the activity of its central black hole. Imagine a young galaxy in the early universe teeming with gas and dust. At its core, a nascent supermassive black hole begins to exert its gravitational pull, drawing in surrounding material. As this matter spirals inward, it heats up, emitting vast amounts of radiation that can either fuel star formation or suppress it, depending on the intensity. This feedback mechanism plays a crucial role in shaping the galaxy's destiny. For instance, when a black hole becomes exceptionally active, releasing torrents of energy through jets and winds, it can expel gas from the galaxy entirely, halting further star formation. Conversely, less intense activity might gently stir the gas, encouraging new stars to form. The symbiotic relationship extends beyond mere energy exchange. Observations reveal that larger galaxies tend to house more massive central black holes, implying a deep connection between the two. Scientists believe that as galaxies merge over time, their central black holes also combine, growing even more immense. These mergers trigger bursts of star formation while reshaping the galactic structure, creating elliptical galaxies from once spiral-shaped ones. Understanding this interplay offers profound insights into the life cycle of galaxies. It helps explain why some galaxies appear quiescent, having exhausted their star-forming resources, while others remain vibrant hubs of stellar birth. Moreover, studying the feedback processes could reveal how galaxies regulate their growth, maintaining a delicate balance between creation and destruction. As researchers continue to probe the link between supermassive black holes and galaxy evolution, they uncover clues about the fundamental forces driving cosmic architecture. By unraveling this mystery, we not only gain knowledge about black holes, but also deepen our appreciation for the intricate dance that shapes the universe's grand design. Shifting our focus from the cosmic dance of galaxies and black holes, let us now delve into one of the most captivating speculative theories surrounding Tabby's star, the possibility of alien megastructures. This enigmatic star, formerly known as KIC 8,462,852, has puzzled astronomers since its discovery due to its unusual dimming patterns, which cannot be easily explained by conventional astrophysical phenomena. The idea of alien megastructures emerged as a bold hypothesis to account for these peculiar fluctuations in brightness. Imagine an advanced extraterrestrial civilization constructing vast structures around their star to harness its energy, a concept reminiscent of the Dyson sphere proposed by physicist Freeman Dyson. Such a structure could theoretically block light from reaching Earth-based telescopes, creating the observed dips in luminosity. While intriguing, this theory remains speculative for several reasons. First, there is currently no direct evidence supporting the existence of such megastructures. Second, alternative explanations like swarms of comets or dust clouds are more consistent with available data. However, the allure of the alien megastructure theory lies in its ability to spark imagination and push the boundaries of scientific inquiry. It challenges us to consider what might exist beyond our current understanding of the cosmos. Moreover, the search for signs of intelligent life through phenomena like Tabby's star highlights humanity's enduring quest to answer one of the universe's greatest questions: are we alone? Even if the mystery ultimately finds resolution in natural processes, the investigation itself enriches our knowledge and fuels innovation in astronomy. By exploring these speculative ideas, scientists refine techniques and technologies that may one day uncover definitive proof of extraterrestrial civilizations, or deepen our appreciation for the complexities of the universe. This blend of science, speculation, and curiosity keeps the fascination with Tabby's star alive, inviting everyone to ponder the possibilities hidden among the stars. Moving beyond the speculative allure of alien megastructures, let us now turn our attention to a cosmic enigma that intertwines with the very fabric of the universe itself: the profound connection between the Great Attractor and dark matter. While the Great Attractor is a gravitational anomaly pulling vast clusters of galaxies toward an unseen mass deep in the universe, dark matter remains the invisible scaffolding that shapes the large-scale structure of the cosmos. Understanding their relationship could unlock some of the universe's deepest secrets. The Great Attractor's pull is so powerful that it influences the motion of our Milky Way and countless other galaxies. Yet, its exact nature remains elusive. Scientists believe that much of this mysterious attraction may stem from the influence of dark matter, which constitutes approximately 84% of all matter in the universe. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light, making it nearly impossible to detect directly. However, its gravitational effects are undeniable, and they provide crucial clues about its role in phenomena like the Great Attractor. Dark matter forms vast halos around galaxies and galaxy clusters, acting as a kind of cosmic glue that holds these structures together. In the case of the Great Attractor, dark matter may be responsible for creating the immense gravitational well that draws everything toward it. By studying how dark matter interacts with visible matter and radiation, astronomers hope to pinpoint the location and distribution of the hidden mass behind the Great Attractor. This investigation could reveal whether the phenomenon is primarily driven by conventional mass concentrations or if dark matter plays a dominant role. Moreover, understanding the interplay between dark matter and the Great Attractor has broader implications for cosmology. If scientists can determine how dark matter influences such large-scale structures, they may uncover fundamental insights into the formation and evolution of the universe. For instance, the distribution of dark matter might explain why certain regions of space exhibit higher densities of galaxies, while others remain relatively empty. In essence, unraveling the mystery of the Great Attractor offers a unique opportunity to probe the properties and behavior of dark matter. Conversely, advances in dark matter research could shed light on the forces driving this colossal gravitational anomaly. Together, these investigations highlight the intricate dance between visible and invisible components of the cosmos, reminding us just how much there is still to learn about the universe we call home. As technology improves and new discoveries emerge, the connection between dark matter and the Great Attractor may become clearer, bringing us one step closer to solving two of the most compelling mysteries of modern astrophysics. Shifting our focus from the gravitational mysteries of the cosmos, let us now delve into one of humanity's most ambitious quests: the search for extraterrestrial intelligence, or SETI. This endeavor represents a bold attempt to answer one of the most profound questions in existence. Are we alone in the universe? At the heart of this search lies the challenge of interpreting potential signals from alien civilizations, such as the infamous WOW signal. The WOW signal, detected in 1977 by astronomer Jerry Amon, stands out as one of the most intriguing and unexplained transmissions ever captured. This 72-second burst of radio waves originated from the constellation Sagittarius and exhibited characteristics consistent with an extraterrestrial source. Despite decades of follow-up observations, no repeat signal has been found, leaving scientists puzzled and eager for more data. Beyond individual signals like the WOW, SETI efforts face numerous challenges that complicate the search for intelligent life. One major hurdle is the vastness of space itself. The sheer scale of the universe means that even if intelligent civilizations exist, their signals may be incredibly faint, distorted, or lost amidst the cosmic noise. Additionally, Earth's atmosphere can interfere with incoming signals, requiring sophisticated technology to filter out false positives. Another significant challenge lies in distinguishing natural astrophysical phenomena from artificial transmissions. Many celestial objects, such as pulsars and quasars, emit powerful radio emissions that could mimic alien broadcasts. To overcome this, researchers must develop advanced algorithms capable of recognizing patterns indicative of intelligent design while ruling out natural explanations. Furthermore, the question of what constitutes a message adds another layer of complexity. If an alien civilization were to send us a signal, would we recognize it? Would it resemble anything familiar to human communication methods, or might it rely on entirely different principles? These uncertainties underscore the importance of interdisciplinary collaboration, bringing together experts in astronomy, linguistics, computer science, and other fields to tackle the problem from multiple angles. Despite these obstacles, SETI continues to evolve, driven by technological advancements and renewed enthusiasm. Modern telescopes equipped with cutting-edge receivers allow scientists to scan wider swaths of the sky at unprecedented sensitivity. Initiatives like Breakthrough Listen have injected fresh resources into the field, enabling large-scale surveys across millions of stars. Ultimately, the search for extraterrestrial intelligence serves as both a scientific pursuit and a philosophical exploration of our place in the cosmos. Whether or not we ever detect definitive proof of alien life, the journey itself enriches our understanding of the universe and inspires generations to look beyond the confines of our planet. As we continue to refine our tools and techniques, the possibility of making contact remains tantalizingly within reach, fueling hope and curiosity alike. To wrap up our journey through the cosmos, let's take a moment to reflect on the 25 unsolved mysteries we've explored together. From the enigmatic nature of dark matter and dark energy to the puzzling phenomena of fast radio bursts and gamma-ray explosions, each mystery paints a picture of a universe far more complex and intriguing than we could have ever imagined. These cosmic puzzles remind us just how much there is still to learn about the vast expanse beyond our planet. The search for answers drives humanity forward, pushing the boundaries of science and technology in ways that benefit not only astronomy but countless other fields. Every discovery, no matter how small, adds another piece to the cosmic puzzle, bringing us closer to understanding our place in the universe. Yet, as we've seen, some questions remain stubbornly unanswered, challenging us to think deeper and look further. As we stand on the brink of new breakthroughs, it's exciting to ponder which mysteries might be solved next. Will we finally unravel the secrets of dark matter? Could we one day detect definitive proof of extraterrestrial life? Or will the origin of supermassive black holes reveal itself to us? The possibilities are endless, and with each passing year, our tools grow sharper and our knowledge expands. But exploration isn't just about finding answers, it's also about asking the right questions. It's about embracing curiosity and daring to dream beyond what we currently know. So, as you watch the stars tonight, consider the wonders hidden among them and the role you might play in uncovering them. After all, the universe belongs to those who seek its truths. If this video has sparked your interest in the cosmos, don't forget to hit the subscribe button, like the video, and turn on notifications so you never miss an update. Together, let's continue exploring the infinite mysteries of space.